Sorry, I forgot to activate the audio on Zoom. I think we can start. Okay, so this is lecture number 5, yes. So we are about midway of our interaction. And yeah, I notice now that in my webpage, the room is still the old one. And unfortunately, I will make a change to it. And what are we talking about today? So first of all, let me share the screen. Here we are. Good. And today we will talk about the history of Earth's climate. So we are skipping for now the lecture on climate change and water cycle, because I thought that it's better to anticipate the general lecture on the history of our climate in the far past. And then I will focus specifically on the water cycle later. So I just inverted the chronology of these two lectures. Now, if you click on this link on my website, History of Earth's Climate, you are redirected to Virtuale. And the reason is that I am using the slides of a colleague, just 1 second, I log in, who prepared these slides. She's a geologist, well-acknowledged geologist. And given that I'm using her slides, I'm not sure they are public domain, and therefore I prefer to make them available through Virtuale. Indeed, if you follow the link into Virtuale, you will find, just 1 second for the upload, you will see the same lecture, History of Earth's Climate, and the slides are given in the second link. In the first link, you have some papers that a colleague provided to me if you want to study more on what we are discussing today. So by clicking here, you will see that presentation comes out, and let's then follow this presentation. Just 1 second, I'm putting it on the desktop. Okay. I prefer to visualize it with Acrobat Reader. Very good. Okay, so this is a fascinating lecture today, trying to explore the past history of our climate. It's a long history because, as you know, the history of Earth is about 5 billions of years long. And of course, we cannot reconstruct everything in the past. We can go anyway quite far in the past, even in the past before the advent of humans and of humans over the Earth. So we can go back much further than that. And the way we go back, as we will see today, is through the analysis of remains of the past climate. Remains, it's a very generic term. We will see in detail what kind of signatures of past climate we can use to explore what happened in the past. This is, of course, a very useful information. As you can read over this slide, on this title slide, the past, it's written, he's the savior for the future. So gaining a better understanding of the past, of course, allows us to improve our capability to predict the future, our capability to provide an interpretation for the present and a prediction for the future, because it's information on how the climate system works, and information that it is potentially very extended in time and therefore can account for very infrequent events, and the time that it took to the Earth system to recover after these shocks, after these perturbations. And also it allows us to understand the history of the past climate in terms of energy that the Earth received from the sun, and in terms of the evolution also of the life over the Earth, which is interacting to some extent with climate. And this is, of course, an indication, because it is true that the past is a unique trajectory, and we are not sure that the future will be analogous to the past, or we can say for sure that it will not be analogous, because the context is different, everything is evolving, the solar system itself is evolving, the sun is evolving, evolutions that in the short term are negligible, but in the long term are very significant. On the other hand, it's clear that an understanding of the dynamics of these evolutions in the past allows us to make predictions, also taking into account that our aim is to make prediction, first of all, for the near future. We aim to predict the climate, as you know, up to 2100. And it's a time span of 8 years. It's nothing compared to the time span already covered by Earth in its life. So in this short period, if we gain a correct interpretation of the present, we gain a lot of capabilities in order to improve our skills to elaborate future predictions. There is one other thing that I want to say regarding the Earth. The Earth is, within the solar system, a planet that has some unique features. And in particular, it is unique, the kind of atmosphere the Earth has. First of all, the Earth has an atmosphere. Not all the planets have one. And the effect of the atmosphere is very multifaceted. So it's a very diverse effect in terms of consequences of the presence of the atmosphere. And first of all, one unicity of the Earth system is the fact that we have the climate system. And the climate system is in a way contributing to modeling the shape of the Earth. And in particular, the climate system is counseling the traces of the past, the traces that the climate itself left over our planet. And I want to give an example. If we look, for instance, at Mars, a planet that we know quite well now, because, you know, we had several missions with landings of machinery that were able to take samples and to explore the planet and take very detailed images of the planet. We now know that Mars was once upon time hosting a great volume of water, an important volume of water, much more than the water that is today present over the Earth, even if Mars has a lower size with respect to the Earth. And the reasons why this amount of water almost entirely disappeared, because we found some traces of water over Mars, but not many, over Mars, but not many, And the reason why the water disappeared are not completely known. And one of the hypotheses is that Mars lost its atmosphere because the planet may have lost the magnetic field. And the reason why the magnetic field went away is probably the fact that the nucleus of Mars got colder and colder. The magnetic field is originated by the fluidodynamics of the nucleus of the planet over the Earth. It's the circulation of material in the nucleus that is activating and originating the magnetic field. So we know that for sure with the increasing age of the planet, the nucleus is going to getting colder and therefore it's going to solidify. And probably this solidification of the nucleus of Mars caused the interruption of the magnetic field. The magnetic field is like a screen against cosmic rays, against radiations coming from the sun. And there is the possibility that these cosmic rays broke the molecules of water and provoked the scission of the molecules of water into hydrogen and oxygen. And this may have caused the disappearance of water over Mars. And the fact that Mars doesn't have any precipitation anymore, doesn't have an atmosphere, is the reason why we can see so many craters over Mars. Now we know the morphology of Mars, and we can observe several craters. And these craters have partly canceled the signatures of river valleys. And the craters are originated by the collision with asteroids, with meteorites. And this is something that is not unlikely in the Earth system, in the solar system. There are several asteroids that are occasionally hitting against planets. And some of these asteroids are very huge. And their signature are these craters, which are so numerous over Mars. Over the Earth, we were able to identify only a small number of craters induced by collision with asteroids. But the reason is not the fact that the Earth is less exposed. The reason is precisely the fact that the presence of the climate system over the Earth canceled the signatures, the footprints of these collisions. So what is the moral of the story? The moral of the story is that any planet in the long term, in the time scale of billions of years, has a huge probability in the long time to be hit by asteroids that are very large. I mean, the size of the craters over Mars is impressive. Some of them are really huge. It means that also the Earth is exposed to that. It's something that may happen also in the future. Probably didn't happen in the past some millions of years, not in a very, I mean, in a disastrous manner. We had some collisions, but very minor entity. And the fact that it didn't happen in probably the last maybe millions of years does not mean that it may happen into the future. And these kind of events are impacting the climate system in a strong manner. We will see that they have the potential of completely changing the climate, and maybe that these events were the causes of some of the glaciations, because they may originate indeed huge perturbation. They may change the inclination of the Earth's axis. And these events, these space events, may also cause some changes in the complete Earth system, may cause a mass extinction. At least it is something that we can predict, but if with some anticipation. But being able to predict them doesn't mean that we can avoid these collisions, and there is no way currently to avoid them. How can we destroy an asteroid with a huge dimension? And these considerations, I make these considerations because I want to make you aware of the importance of the time scale. When we talk about the history of the Earth climate, we shift to a different time scale with respect to climatic predictions, which operate over a time scale of 8 years. And it looks like for us, it's a huge, a long time scale. It's not, if we look at the history of planets. It's not if we look at the history of the solar system. It's absolutely nothing. I mean, 1,000 years, even 1 million years is nothing in the time scale of the solar system. And of course, we are mainly concerned by the next time, the time of the future generations. And when we say future generation, we don't think at 1,000 of future generations. We think at 4 or 5, maybe future generations. So we are interested in this time scale, and during this time scale, the risk associated to a collision with an asteroid is really minimal. And on the other hand, in the very long time scale, this risk increases. Okay, so let's focus on the details of our lecture today. And this is just a summary, and I think we can skip it because I'm not sure we can get to the end of this list of slides. Of course, what matters for your preparation, for your study, is what you can find here and we discussed today. So in order to prepare for the exam, to be very explicit, look at these slides, especially at the details that I will point out to you, and look at what we are completing today. Now, first of all, this is the reconstruction of the past climate is typically a discipline that belongs to the field of geology. It's also part of climate sciences, but it is typically a cross-disciplinary or interdisciplinary field. The climatic reconstruction or paleoclimatic reconstruction, we add paleo because we refer to very ancient times. As I said, this is a cross-disciplinary field, and the means that are used are the same, and we will see how we reconstruct the past climate. On the other hand, the interpretation leaves room to some subjectivity, and the interpretation is to some extent different. And therefore, it is important that we try to refer to multiple sources in order to reduce the uncertainty. Here you can see an important quote of geologist Charles Lyell, who wrote an important book in around the mid of the 19th century, introducing the theory of uniformitarianism. The present is the key to the past. So basically, the uniformitarianism assumes that the physical laws and therefore the dynamics of the processes that we can observe today is the same that was underlying what happened in the past. So basically physical laws, fluid dynamics, and climate physical laws, climatic laws, it is assumed that they held in the past as they hold today, which is quite understandable, quite reasonable. On the other hand, it's an assumption because I mean the environment over the Earth have been very different in the past. Even if the laws were the same, the forcing may have been completely different, and a completely different forcing may induce to a completely different reality, even under the same laws. So it is an assumption that doesn't imply that the present is a good mirror for the past, because the conditions could have been completely different. And indeed, this is something that this approach based on uniformitarianism is typical in geology. But on the other hand, you will see when we derive interpretations based on what we observe today, interpretation of the past dynamics of the Earth system, there is some subjectivity. So here you see a picture of the Scala dei Turchi at Agrigento in Sicily, which is a very important geological record. You see the stratification, and it gives already to you an idea, first idea of what signatures we can use to understand past climate, to reconstruct past climate. These layers are sedimentary layers, and these sediments incorporate several remains, which we will try today to decipher. We know already that geological formation bring knowledge about the past. Indeed, when we subdivide the history of the Earth in eons, eras, and epochs, ages, we base this subdivision on geological signatures, on geological stratigraphy, for instance. And basing on the traces that we find in these geological signatures, we separate the ages, epochs, periods, and eons. We will see some more details. So the separation again between these time periods, paleoclimatic time periods, is operated on the basis of stratigraphy. And so you understand why an evidence like the Scala dei Turchi is important. So I want, before I move forward, let me just anticipate this slide, and then I'll go back to the previous one. This is a diagram of the past that we are going to study, with the subdivision in eras, and the eras are for instance, the Paleozoic, the Mesozoic, and the Cenozoic. And you see that each era is subdivided into epochs. So the Cenozoic is the current era, which includes the Paleocene, and you see the time scale on the right, about more than 60 millions of years ago. Eocene, Oligocene. At the Oligocene, we are at about 30 millions of years ago. Miocene, Pliocene, Pleistocene, and Holocene. Holocene is the current epoch, and the Holocene goes back to about 10,000 years ago. So the time scale is not linear, and then it arrives up to today. Okay, all of these periods, or sorry, all of these epochs are identified based on geological signatures. Now, you know that about 15 years ago, Paul Crutzen, famous scientist, proposed the introduction of a new epoch, the Anthropocene, while that is defined as the epoch which is heavily influenced by the presence of humans Actually, this introduction of a new epoch is a bit questioned because we cannot identify a geological signature of the presence of humans on the Earth. I mean, the Holocene was identified because about 10,000 years ago, as we will see, the temperature over the Earth started to increase after the last glaciation. So after the last minimum, the temperature started to increase, and from 10,000 years ago up to today, the increase was quite important, was very rapid. And therefore, you can really identify the geologic signature For instance, the sea level increased about 120 meters, as we mentioned some time ago. And you can clearly identify signatures. And while we still cannot identify geologic signatures of the introduction of a new epoch, the Anthropocene. So it is a big question. On the other hand, we can also say that the presence of humans over the Earth probably has never been so massive, so intensive. I mean, the signatures over the Earth system of the presence of humans probably that we observe today is probably unprecedented. On the other hand, we can also say that the whole Holocene has been characterized by an increasing human signature. Because, as you know, the humans, the first traces of humans, what we can call humans, was a completely different kind of human, but it dates back to about 7 million years ago. So it goes back to the Pleistocene and the Pliocene to some extent. And during the Holocene, this presence of humans, and we know that from our knowledge of history, became progressively more and more impactful over the Earth system. It is true that in the past 100 years, the gradient of the impact, if we can use this term gradient, became probably unprecedented. So the changes that we are observing now are probably unprecedented. On the other hand, it's also clear that we cannot say that humans started to affect the Earth system in a significant way only in the past 30 years. It has been a long history of human impact. And in fact, the previous slide is showing the effect of the great acceleration that we already know, we already mentioned in sea level change, but please look at the scale, millimeters. And so what we can observe after the great acceleration is an increase of about 20 centimeters of sea level, while, as I said, during the Holocene, it has been an increase. We know that there has been an increase of more than 100 meters. And also we see here the temperature anomaly, and we already know these graphs, so there is nothing more to say. And this is the evidence that brought Paul Crutzen to introduce, suggested Paul Crutzen to introduce this new epoch. On the other hand, as I said, you can see here that the epochs are, identified on the basis of geologic signatures. Their duration is millions of years, and the Holocene started just 10,000 years ago. So I think there is the risk that when we focus on over the present or our recent past, we tend to zoom out, or to zoom in, and to consider significant changes that over the geologic timescale are not significant. However, in order to resolve these doubts, we need to understand the past climate. We need to understand what happened in the past. And this is why paleoclimatic reconstructions are so important, are so fascinating. But what kind of data can we use? We already mentioned that we can use proxy data. We mentioned tree rings, we mentioned ice cores. So let's look at more details, because the reality of the interpretation of these signatures is much more complicated and fascinating than just looking at the width of tree rings. There is much more in that. So let's try to find more details. And this is an important reconstruction that has been completed about, it was presented in Science 5 years ago. And it has been obtained by using several proxy data. I'm using this reconstruction to get a first clear picture of what we are talking about. In terms, this is showing fluctuation of temperature. And this video basically dates back to 500 millions of years ago. There has been several other reconstructions that have been completed before this one, but this is quite unique for the extension of the reconstruction. You can see numbers here. Wait a couple of slides because this picture is kept also in the next two slides, and in the third one you will see the meaning of the numbers. For now, let's focus on the main feature, and then we will see the meaning of the numbers. So first of all, what you see is a dashed line that makes a separation. This is extremely interesting. A separation between the Earth without polar caps above in orange and the Earth with polar caps in blue. And this separation is around a global temperature of, I would say it's midway, it's about 18 degrees of global temperature. Now we are around, as we know, 14 degrees. 14, and we still have to reach 15. So it looks like this reconstruction is telling us that we still have like 3 degrees of margin before getting to the melting of the polar caps. The melting of the polar caps, I wanted to say, the polar caps, however, were present over the Earth for a limited time period, as you see, compared to the whole history. So it was longer the time without polar caps than the time with polar caps. And in the past, we had the presence of polar caps for about more than 10 million years already. So in order to find a temperature such that the polar caps disappear only for a small time frame, as you see, there is a very tiny peak, orange peak there. We have to go back about 15 millions of years. And we can also say that for the past 40 millions of years, we almost always had the polar caps. And this is the last glaciation that peaked about, the minimum of the temperature was reached about 30,000 years ago. We will see some more refined graphs. And from 11,000 years ago, we had this sharp increase that you can see in the right tail of the figure. You can see quite a sharp increase of temperature. So this information that we may still have 3 degrees, it's interesting. And of course, it's not a final information because it doesn't mean that, it doesn't mean that this is precise, first of all. There is uncertainty in these reconstructions. But even if it was precise, it doesn't mean that uniformitarianism applies strictly. So it doesn't mean that what's happening today will be the mirror of what happened in the past. But still, this is an important indication. Another important indication that we can see here is that indeed we are in a cold period. We are in a kind of, we are under the effect of a kind of cold house effect. Okay. And let's now get some more information here. So you see the separation between what is called the greenhouse condition without polar caps and ice house conditions. Keep in mind that humans go back, as I said, about 7 million years. So humans knew the Earth in the current conditions. Humans, what we mean for humans didn't exist 50 millions of years ago when the Earth was not covered by ice caps, when the average temperature was kind of 25 degrees, which means 10 degrees more than today. we know that life probably existed over the Earth in that conditions, but on the other hand, probably it was a kind of elementary life. So the question is whether the humans could survive in a planet that is 20 degrees of average temperature without polar caps, which means a completely different ocean. It means a higher ocean and completely different because it would be warmer and warmer with a lot of CO2 released by the oceans. So would the Earth be habitable anyway? This is the big question which we are trying to understand. And the first step is understanding what happens in the past, as I said, what happened in the past, as I said. Now, here you see the definition of the numbers. So indeed, number one marks the Cambrian explosion during a very high temperature period where we know there was some marine life already. And we know that life over the Earth was already existent about 5 millions of years ago. 500 millions of years ago. Now, number two marks the beginning of a very long period, about 200 millions of years, during which polar ice caps formed and persisted for a long time. The temperature was like average temperature to 10 degrees. Keep in mind that 10 degrees compared with the current 15, a little bit, let's say after global warming 15, means a lot in terms of glacier expansion. So we get glaciers reaching the city of Verona. I mean, 5 degrees less would mean something really important and something that was barely experienced by humans. And keep in mind that during this very cold period, humans migrated in warmer area over the Earth for obvious reasons, because these climatic changes trigger migration. Then, after this cold period, after this glaciation, there was an increase of temperature, which caused some mass extinctions. And for instance, with the number 3, you see marked here the radiation of reptiles during a greenhouse period, because of course, when you get extreme conditions, the most evolved forms of life tend to get extincted, while the elementary forms of life have a higher chance of surviving. So we think that these reptiles were indeed, this is one of the assumptions, the extinction was caused by an increase in temperature. And keep in mind that older humans and these older and even older forms of life, they didn't have any, they have reduced means to adapt. I'm not saying any, because I mean, there are forms of adaptation, for instance, migration that can be operated also by, can be taken also by elementary forms of life. But of course, today we have means to adapt that are much larger, even if much important, much effective, I wanted to say, even if you understand that these forms of adaptation cannot be adopted in a uniform way by the whole human population. There are zones in the world where there are more efficient capabilities to adapt to climate change. There are areas in the world that are more exposed to climate change and where the capability to adapt is perhaps lower. So, I mean, adaptation would be anyway something that has to be paid with a cost and with migrations, etc. Number 4 marks another great extinctions, great extinction of mammals, and the animals with bigger size suffered more from this extinction, like in any extinction. And then we got into a new glaciation, which is marked by, the minimum is marked by the number 5. And then, starting from 10,000 years ago, looking at a different time scale, we observed this increase of temperature from 10 degrees to the current value of about 15, with the advent of global warming in the past 30 years. 30 years compared to 500 million. You understand that we are trying to provide an interpretation for something that is like a drop in the ocean of the time scale of the history of Earth. 30 years is like a drop, or less than a drop, I would say. And it is something that it is really difficult to say over this time scale if it is a big change or a small change. It's really difficult after only 30 years to be able to say if this change will last for a long time or not. Of course, we have scientific interpretation also, and the scientific interpretation is that this is caused by humans, and as such, this interpretation supports the idea that is something that will continue and probably will become more and more impactful. But you understand that when you look at data over a so large time scale, at information that may be significant for a large time scale, the same information may be less significant when we look at very tiny time scales. Okay, so this card was constructed by analyzing several paleoclimate archives and several paleoclimate proxies. So what are paleoclimate archives? What are paleoclimate proxies? Where we should search a good archive and how we should study it? These are interesting questions. So this is another picture of an interesting sequence of layers, Monte San Nicola in Sicily. There are several geologic signatures in Italy, interesting geologic signatures. And the reason is that the morphology of Italy is quite complicated. We have a lot of mountains, and we have an environment that is subjected to shocks like landslides, like floods, like earthquakes. And these shocking events often bring to the light what was previously buried. And we have an active erosion in Italy, an active deposition of sediments. So, of course, also in the past, the situation was similar, and therefore it's a very active environment that keeps a long track of what happened in the past. And the paleoclimatic archives consist of geologic or biologic materials that preserve evidence of what happened in the past. And examples may be rocks, like in this case, sediments, also like in this case, because these rocks are showing layers of stratification. Corals are an important climatic signature. We will see why. Ice, and ice carols deliver a lot of information. Tree rings. Now, here I want to show an example of signature that can be derived, signature of past climate, from ocean drilling. What you see here is a boat that is used to drill carrots from the bottom of the ocean. The bottom of the ocean brings information because, of course, it is also made by stratification of sediments, and in particular fossil of living species like corals, like foraminifera, etc. And by looking at the succession of layers, succession of sedimentary layers at the bottom of the ocean, we can get an idea of the time scale. And by looking at the content of each layer, we can get an idea of the climate, and in particular of the temperature. How? We will see. And first of all, what you see here is a picture of the IODP International Ocean Discovery Program. And you see how many drills we already realized. I want to show you this video. Just 1 second, because I think we don't need to share the audio because there are subtitles. And okay, there must be some advertisement. Oh, okay, it's no more available. I think, just 1 second, because I don't think so. I think it's still available. Let me see. Yeah, okay. The reason is that, let me see if I can make a selection of it. Okay, copy. I think it's still available. No, still. Okay, let's forget about it. No problem. And then let me see if I have, okay. It's really strange. 1 second. Okay. Let's see. No, okay. It's really strange because I am convinced that I looked at it like a couple of months ago, but maybe. Okay, but anyway, it was just a video. It was a dissemination video showing how they make these drills and how they take the cores. Basically, they use a boat like this where by percussion, they put this very long tube with an excavating mechanism at the end of the tube. They press it over the bottom of the ocean, and you see that the tube keeps inside it the sequence of the layers of sediments. And then when it is loaded into the ship, they extract the sediments and put them over a table where they create a sequence of sediments of different composition, and this sequence of layers is then dated. This is an example of a manual drilling. And you see here an example, a picture of some of a stratification of sediments. And they can, by knowing the timing of some of these layers, they can date some of them. And then by looking at the width of each layer of sediments, they can build a chronography of this stratigraphy. They can date each layer with reasonable precision. This is a picture of a tree ring, but the key here is to elaborate an interpretation of the content, because the timing is relatively easy to be assigned. Like for 3 rings, 1 ring is 1 year. So it's relatively easy to count them and to date each of them. It's the content that delivers a lot of information that is relevant. It's the information that we want to get. And extracting this information is not trivial. Okay, so let's try to learn something more. Here is another example, and is the ice layers. These are drilled typically in the ice caps, and the carrots of ice are extracted and brought into a frozen room. And then the carrot is preserved into fridges, and the composition of the ice at along the depth is analyzed in detail. In some cases, they can also decipher the seasonal variability. We will see how, but it can be deciphered because the content, the material that is trapped into the ice, I use the term material, but we will see that it's material may be not the correct term, because in some cases it's an isotopic content, which means the presence of stable isotopes. We will see what these are into the ice. This sequence, this material is not only varying along the years, but it is also varying in a cyclic way during the year. So in the intra-annual time scale. So we can identify some periodicity by looking at the cyclicity. So when we see that a cycle is completed, it's 1 year. So we can separate year by year by looking at this seasonal cyclicity. And then by looking at the pattern of cyclicity, we can understand how seasons were different from each other. So it's really a lot of information that we can derive from ice cores. Oh, sorry, I went back. And this is a picture of the global paleoclimate archives. And for instance, if we look at this website, which I'm not sure maybe that we already looked at it, this is the Paleoclimatic Archive of the National Ocean and Atmospheric Administration of the United States. Let's give it some time. So here we can launch an interactive map or a search tool. If we launch an interactive map, you can search for a location, and then the map shows what kind of archives, of paleoclimatic archives, you can find in the given location. So for instance here, if we look for Bologna, just 1 second, that we wait for the completion of the upload. It takes a while. Anyway, given that I searched for it about a couple of days ago, if you search for Bologna, you can see that around Bologna there are some paleoclimatic archives, not really close to Bologna, but in the Apennines, from 3 rings. It is a bit low now. Let's see. Okay, so Bologna. Let's see if we can, Bologna, Italy. Here we are, and then we need to zoom out. And if you zoom out and wait a little bit, let's see. After some time, you should see over the map. Oh, here you see some a paleoclimatic archive here. It's a tree ring. You see the legend on the left, tree ring, and it's close to Pavullo nel Frignano. Probably here there was a very old tree, and you can get the data. And you cannot get the data directly from the map. You should go in the search tool and put the name of Pavullo nel Frignano, and you get to, or you may search for tree rings, and you get at the end a table with data. One second. Here we are. Anyway, there are also websites that can automatically perform the reconstruction of past climatic features. So you put Bologna, and they automatically select the proxies, the paleoclimatic archives that are closer to Bologna, and they make already a mix. And these tools are open access. So if you search for paleoclimatic data, you find a lot of information. It is more difficult to use these tools rather than this is the main obstacle, not the availability, not the presence or not of the data. The data are there, but of course, given that these are huge databases, using them it's not difficult, but it's not really straightforward. Okay, so what kind of archives can we use? Marine sediments, we already talked about it. Ice cores, speleothems, and speleothems are the signatures that you can find into the caves. You know that caves bring a lot of information because there are structures there, stalagmites, for instance, that develop in the very long time, and their composition delivers information on the past climate. And also important, the lacustrine sediments, limnology. Limnology is the basis for several paleoclimatic archives. Lakes deliver a lot of information. And what are the proxies? The proxies are now in yellow here. So for marine sediments, we analyze, this is the information that is interesting to know, the chemical composition, stable isotopes, we will see what stable isotopes are, particle size, fossils as pollen and spores, and micro and mediofauna and malacofauna. For lacustrine sediments, again, it's more or less the same thing. And then we have speleothems stable isotopes. And for ice cores, the dust is a signature of past perturbations like volcanic eruptions, gas concentration, again, volcanic eruptions, composition of the atmosphere, and then stable isotopes. You see that stable isotopes are everywhere. Indeed, stable isotopes are probably the most used signature of past climate. It's very interesting to see how we analyze them and why they are meaningful. Okay, so paleoclimatic proxies, we can classify them in direct or indirect proxies. The direct proxies deliver information in terms of atmospheric gases trapped in the layers of the ice cap, for instance. And for the indirect information, we need calibration. What is calibration? Calibration means that you observe something that is not directly related to climate, and we connect this something not directly related to climate to climatic variables through calibration, through a transformation, an analytical transformation, which includes, it is flexible, includes parameters. It's a parametric function. Parametric means that it includes parameters. Parameter means something that needs to be tuned, to be calibrated, okay? And of course, the direct information delivers instead directly a climatic variable like atmospheric gases, which are an indicator of climate, a direct indicator of climate. So of course, the direct information is preferable, but on the other hand, it is also the indirect information. It is very useful because it provides additional and redundant information that can be used to calibrate, to adjust our evaluation. So the curve that, the only curve that so far I showed to you of past reconstruction of temperature was derived by putting together a lot of different information. Okay, so here you see an example of an ice core that is treated in the lab. And now let's look at this further reconstruction, and which was derived by this ice core in 1999. This gives back to 400,000 years ago, 500,000, not much. It gives the CO2 concentration. And what we can see here, it's something that we already know. The current level of CO2 concentration is larger than any other peak in the past 600,000 years, which is, as I said, something that we already knew. That is to say that if you remember the progress of the Earth's temperature, 500,000 of years, we are still into the, how they called it, ice, cold house period. So this record doesn't extend back to the greenhouse period without ice caps. And so it would be useful to know if when temperature was much larger than today, what was the CO2 concentration? Actually, we already know that the CO2 concentration in the very far past was much higher than the current CO2 concentration in the atmosphere. On the other hand, you understand that what is the value of ice cores? Basically, this information, it is shown now because it was derived directly from an ice core by looking at the concentration of CO2 trapped into the core. And a single core, as you see, this one is the Vostok drill, delivers really an important information. Let me see over the web if I can find something more. Vostok ice core. You see how many entries? Wikipedia, Vostok station. And this is where the station is located. Station established in 1957. It's a drilling station. And let's see if we can get some reconstruction here. No, this is current climate. And you see here the several reconstructions. And the depth of the core reaches 1 kilometer of ice. Okay, this figure shows different concentration of different gases. This is methane, this is insolation, and this is CO2. And here there is a temperature time scale that was derived corresponding to the different signatures. There are several links. See here, Vostok ice core. Let's see if we can find some pictures. These are the reconstruction. You see here CO2 in the ice core record. I think you can just put the video for a little. Okay. Okay, here we are. So let's move forward. Here there was another YouTube link, but we already found it by ourselves. Just 1 second. Okay, good. And I think we can, here we can see a map of several core stations. Vostok is here, and then there are other stations, as you see, because there are several experiments that are being done. And by the way, to ocean drilling and ice caps drilling are dedicated several research projects every year. There are a lot of missions that are operating, and a lot of missions are continuously activated to retrieve more information. This is is considered to be one important research challenge, reconstruction of past climate. And we are still getting a lot of new information on that. So now, isotopes, stable isotopes. This is interesting. And if you look for paleoclimatic archives, you will encounter many times this terminology, stable isotopes. What does that mean? So let's go back to our Google page, and let's look for stable isotopes. Wikipedia, stable nuclide or nuclide, depends on the pronunciation. And anyway, let's follow this definition. Okay, first of all, you see a warning here, additional citation for verification. So be careful about these warnings. I think we already discussed that Wikipedia, I consider Wikipedia in English a very reliable source, but it's important that you look at the warnings, because Wikipedia is it's a community effort. And Wikipedia is not commercial, it's not paid, it's built by people like us. And it's built by users. And therefore, warnings are important, because in this case, you understand that some people, some users think that additional citations are needed. So stable isotopes are nuclides, or nuclides, you know what the nucleus of the atom is, that are not radioactive. And so, unlike radionuclides, do not spontaneously undergo radioactive decay. So basically, stable isotopes are stable. So they keep the same form of the atom. And therefore, given that they don't undergo any alteration, we can assume that the current isotope that we find in an ice core, for instance, is the same that was trapped when the ice formed. So there was no change of the isotope, because the isotope is stable. Okay. There are several elements that include one or more stable isotopes. And I want to give you an example. Oxygen has two stable isotopes, or I think three, but there are two of them which are called O16 and O18. O16 because the atom of oxygen is composed by 8 protons and 8 neutrons, same number of protons and neutrons. O18 is the nucleus includes 9 protons and 9 neutrons. So it means that the O18, the isotope of oxygen 18, is heavier than the atom of O16. And once again, if we find O18 into an ice core, it's the same O18 that was trapped into the ice core. So it's not possible, because it's stable, that an O18 transforms into an O16. When we analyze an ice core in the ice, or when we analyze a marine sediment in the sediment, we can identify the percentage of O18 and the percentage of O16. And why these differences in percentage are important. Here you see a long discussion on the stable isotopes. I don't think we really need to read everything here. It is an easy reading, and it's an interesting reading. I would say that it's to some extent also fascinating. So I encourage you to read it. But actually, what is important that you keep in mind for our purpose is that, for instance, oxygen, and why I insist on oxygen, because oxygen, the atom of oxygen, is included into the molecules of water. And therefore, it's everywhere, in tree rings, in marine sediments, in ice cores. So it's important that you consider that oxygen can be included into the cores in two forms, two different atoms of oxygen, 18 and 16. They don't transform into each other. 16 is lighter than the heavier 18. This is what is important that you remember in order to keep, to understand why their relative proportion is important. Oxygen is present, for instance, in marine water with both stable isotopes, also with oxygen 17. But what is more important for us is to keep in mind 16 and 18. Okay, why it's important? Let me anticipate some slides here. Let me anticipate this one. This one is what's nice in order to understand. Let's look at the right graph. So first, evaporation from the ocean preferentially is at the expense of O16 because it's lighter. So of course we have also some evaporation of O18, but there is a preference for O16 evaporation. And then in a cold period, you get an ice cap or an ice in glaciers, which is enriched of O16 because it was a dominant evaporation. And therefore, in a cold period where the O16 gets trapped into the ice, the ocean level decreases, and then the proportion of O18 in the ocean increases. So the ocean becomes richer of oxygen 18 stable isotope. So in the marine sediments and in the corals, in the foraminifera, which are the fossils, you find during a cold period more oxygen 18. I mean, I think this is a great discovery, the fact that we can date the sediments based on the proportion of isotopes, of stable isotopes. It's a great discovery. Of course, you get in a cold period more glaciers over the land, and you get this ice that is enriched in O16. And therefore, in a period of increase of temperature, you get a river flow that is higher, usually, or let's say there's a different seasonality, but in any case is enriched during an increase of temperature of O16. So the effect over the land may be different. The effect, it depends on the type of proxy data that you analyze. For a marine sediment, you get more O18 during a cold period. In an ice core, you get, in a cold period, more O16. Okay, so it's different over the land effect. And also the isotopes that are trapped into vegetation, into the three rings, we can also detect the isotopic composition of the three rings. And oxygen is not the only one. There are other stable isotopes that can be analyzed. For sure, oxygen is the most important one. And the way it is analyzed, let me now go back, is through this ratio here. It's an isotopic ratio. So first of all, you see here the slide refers to what is called sigma. This ratio is called sigma O18 and sigma for the deuterium. The deuterium is a stable isotope of the hydrogen. Let's forget about the deuterium. I don't want to give too much information to you, but let's focus on the oxygen. So what you see in the equation below is how the O18 is measured. Is through a ratio. So the ratio, or let's say through a ratio of ratios, at the denominator of this relationship here, I try to put my mouse over. you see the ratio between O18 and O16 in a reference situation. Okay, so the reference situation is the standard mean ocean water. So it's a reference that by convention it has adopted as a mean condition. So this is the ratio between O16 and O18 that you can find in the ocean water in ideal condition. Look at how the isotope is identified with a superscript on the left of the symbol oxygen. Okay, and then you refer at the numerator, there is the difference between the measured ratio between O18 and O16 minus the reference ratio. Again, basically, when the result is multiplied by 10 to the power of 3 for 1000. When the result is negative, you have an ocean that is poorer in O18 with respect to the mean conditions. When the result is positive, it means that the numerator, the first term, is larger than the second term, which means that it's richer in O18 with respect to the standard situation. So by computing this ratio, which is called delta O18 for different time periods, we can estimate for each time period, typically every year, but for ice core is also every season. We can estimate for every season the progress of temperature, because it has been proved under controlled conditions that the delta O18 is highly, for a given ice core, a given type of ice core, highly correlated with temperature. There is a strong correlation. So isotopic composition is something that remains there forever. It's something that is trapped into the ice, into the marine sediments, and it's something that can be associated to a very specific relationship between isotopic composition and temperature. It's wonderful because it also gives seasonal information for the ice cores. For ocean drilling, for ocean drills, not. We cannot identify the seasonal variation. But for the ice core, yes. The seasonal variation in the ocean drills cannot be identified because the ocean has a large inertia. And in the bottom of the ocean, sometimes the seasonal variations are really negligible. Okay, and then you see here another explanation. When data is positive, the sample is enriched in heavier isotope. When data is negative, the sample is enriched in lighter isotope. It is also possible to associate the delta to precipitation. And in particular, let me check, I skipped these two slides, just 1 second, these three, and I go back to the figure here. In particular, you see that there is also a spatial variability of precipitation with depending on the isotopic composition. Close to the coastal areas, you have evaporation from the ocean. Evaporation from the ocean includes preferentially lighter isotope, lighter oxygen, but it also includes some heavy oxygen. The heavy oxygen is more likely to precipitate, to rain down close to the coastline because it's heavier. So it tends to get to the ground faster. It's not transported much by wind. So you get a composition precipitation with some O18. It is an 18, the superscript. It's not very clear, but it's an 18. Precipitation with some O18. Precipitation with less O18. And this is why over the mountains you get more you get an ice that is richer in O16. So, I mean, you can also find a relationship between isotopic composition and precipitation, and in particular, for large precipitation, the isotopic composition tends to be lighter. And it's a relationship that is less strong with respect to the relationship between isotopic composition and temperature, but still it delivers indication. So we can reconstruct temperature and to some extent rainfall. Okay, let me go back with the slides now. So here is an example, temperature from reconstruction of temperatures. And you see here, we go back here about 800,000 years, and you see two graphs. This is temperature in degrees, and this is the delta from the temperature observed in 1950, the global temperature. And you see the variations and the changes are indeed as we expected, because I said that during the last glaciation we had 5 degrees less, and so this is the changes that we could understand that we could detect for the past 800,000 years. And this is similar on the right. It's similar. Okay, it's 800,000 before present. But here the time scale is moving towards our time on the right, and here it's the opposite. It's going toward the past here. But you see that they are mirrored. They deliver more or less the same information. And I mean, it's indeed interesting. Let me see. Okay, before talking about foraminifera, I think it's time that we make a break. Do you have any question? Okay, let's make 15 minutes break. Thank you very much. Okay, we can start. What is your feeling about these lectures? Are you interested? And if you have any critical comment or suggestion or things that you would like to discuss, we still have 3 lectures after today. So I'm really keen on getting your feedback. Usually attendance in presence at these lectures, it's reduced, so it's not for me a surprise. Keep into account that we have 200 students subscribed to this subject, but usually only a very few attend into the room, and also a few attend online, because now we have like 10 persons, no less than that. So it's for me not a surprise, even if it's a difference with respect to the lectures at the courses of engineering. Usually I get a higher attendance, not a full attendance, but higher than this one. But I understand, and I understand that given the nature of these soft skill courses and the character of these lectures, I understand that if one watches the video afterwards, it's more or less the same thing. Of course, you lose some opportunities to interact, but it's more or less the same thing. So I fully understand the students that have other priorities. And also there is to say that this is the week before Easter, so it is quite normal. Okay, very good. Let's move forward now. Foraminifera. What are the foraminifera? They are microscopic sand size dimensions, shell secreting marine organisms. Okay, and they have a very small size, sand size, and they are ubiquitous. They are spread with a very wide distribution, very large distribution everywhere. And basically they form through calcification. They are formed by, it's formed by secretion, and they form their shells through calcification. And many environmental information are incorporated into their body when they calcify, and in particular information on the composition of the surrounding water. So you understand, isotope composition is one thing that gets trapped. The shells are formed by calcite, and the chemical formula is CaCO3. So you see that there are ions of Ca, calcium, and ions of carbon and oxygen. So it is indeed delivering a lot of information, and through their composition. You see that in the deep sea core there are foraminifera trapped into there, because foraminifera then are part of the marine sediments. Of course, you need threshold concentration of foraminifera into the sediment in order to pick up enough information on isotope composition. And the interesting thing is that the sampling frequency is, the time scale on which you can get the information is quite a fine time scale, is year by year, basically. And this is an example of temperature reconstruction that are derived from marine cores and ice cores. And the look at the time scale of temperature is different, because the temperature of the ocean is different from the temperature of the air in correspondence of the ice cores. So if you look at the scale, temperature scale of the ice cores, it's here on the right, from -10 to 8, -12 to 8. And here for the marine cores, the scale is from 4 to 24. But you see that for the same period, you see quite a nice correspondence of the reconstruction. It's really not a one-to-one correspondence, but there is a correspondence. And you understand by looking at these two graphs how the integration of different information from different cores may reduce the uncertainty, because there is a correspondence even if there is a difference in temperature. And you may expect also that the ocean in a way is a filter of the temperature of the air. It's a filter, but still you see that in this there is less variability because the ocean is a filter, is smoothing variability out, but there is a nice correspondence. And this shows the value, once again, of merging information. In general, in climate studies, paleoclimate studies, but also in general, in environmental studies, whatever is the information that you use to support your analysis, it's uncertain. Of course, the uncertainty of proxy data is larger than the uncertainty of direct observations, but still there is uncertainty also in observations. And to reduce uncertainty, one key suggestion is to integrate different sources of information. So you put a lot of sources of information together, and then by merging this information, you come up with a synthesis. Merging the information is, it's challenging. It's a science. It's information theory. How to extract information from data, how to merge, how to make a synthesis. It's a challenge. It's a science in itself. And it's the key to understand nature, to understand the environment, to understand the dynamics of the environment. And this is something that is also in engineering. It's a usual practice. When you work under uncertainty, one imperative rule is to use any information that is available. And it's clear that the information that is delivered by an observation, by data anyway, the information content of a number is different. There are numbers that are highly informative. There are numbers that have limited information, deliver limited information. Some scientists use the term disinformative data. I wouldn't use this term because I think any data is bringing information. Some data may bring a reduced, a very low amount of information. Other data deliver much more information. And it's, of course, you have to weigh the information in a way that you assign more weight to the information that is more reliable. Of course, in words, it's very simple. It looks obvious. Operationally, sometimes it's not so simple. You have to estimate the uncertainty of any number, of any data, and the weight is commensurate to the uncertainty, to the information content. It's challenging, but it's part of science. Okay, and here you see the explanation of why in the shells under cold temperature have a larger amount of O18, of delta O18, and there are actually two effects. First of all, it's temperature in itself. We showed that when temperature goes down, O16 is trapped in the glaciers and the ocean becomes richer in O18. Okay, this is one effect. There is a second effect, which is given by the ice volume. If we have more ice, so I mean, there is, sorry, a direct temperature effect. I made a mix-up of the two explanations. So I start back from scratch, from the beginning. There is a temperature effect. When the temperature is colder, there is a mechanism in the formation of the shells that gives more priority, let me use this term, to the heavier atoms of oxygen. And this is a mechanism that is related to the fact that even with the same isotopic composition of seawater in the ocean, when the temperature is cooler, there is an increase of concentration of O18 into the shells. And then there is the effect of the ice volume. More ice means more O18 concentration in the ocean, and therefore more 18O concentration in the shells. So this is an explanation of this correspondence. So you see that the take-home message, delta O18 records from the shells of a foraminifera provide a quantitative measure of the combined effect of changes in ice volume and in the temperature of ocean water. Ocean basins where sediment deposition is uninterrupted provide continuous records of climate history. If the data O18 is positive, Earth was colder than today. If it is negative, Earth was warmer than today. And here is the picture that I showed you already twice before. This is the graphical explanation of this phenomenon. Good. Now, let's talk about some additional information that can be derived by the course. And in particular, there is a fossil record of climate change in the Mediterranean, which is particularly interesting, and it's given by this kind of shell called Persistrommus latus, which formed in the late Pleistocene, about 130, 110 kilo years before present, so thousands of years before present. And then there is another shell, Arctica islandica, again, which formed in the late Pleistocene in Liguria, in between 18 kilo years before present. And basically these sediments were transported from their place of formation inside the Mediterranean basin, and they are found close to the coasts of Italy. So thanks to this fossil record, we can reconstruct the presence of, the progress of temperature into the Mediterranean and climate change. Okay, so the present day distribution is what you can see over the map. Now, other information can be derived by the vegetation paleo remains and pollen records. This is again important because also vegetation is trapping markers of past climate. And these markers are in the form of stable isotopes or other material that has been trapped, which can be directly or indirectly related to climatic variables with the classification direct and indirect that we mentioned before. And for instance, you see that the pollen that are trapped into the soil, into the remains, are different depending on the climate. So if you look at the Mediterranean forest at our latitudes, if you look at the vegetation at high latitudes, you see very different composition of vegetation. So vegetation is clearly a marker of climate, and also the pollens that are kept trapped into the sediments, into the stratifications are different, and they are a marker of climate change, because you see that in the same place we can find different types of vegetation. And I want to give you an example, a very recent example that is based on oral traditions, oral witnesses over the Alps. We know from the passing of oral witnesses and from the minutes, the diaries taken by monks, that the vegetation over the Alps in the past 1,000 years changed a lot. There were changes in the distribution and type of vegetation. And of course, in some of the cases, vegetation is also influenced by human activity. For instance, wars typically cause a clear cutting of forests because people need resources. And then after the war, in a period of peace, the vegetation is reinstalled. But on the other hand, it's also true that if you look at high altitudes, the influence of humans is less pronounced. So we have, from, as I said, from the diaries of monks and from oral witnesses that were passed generation by generation, we know that, for instance, during the Middle Age, around 1100 after Christ, we got the altitude of woods in the Alps. The limit of the vegetation in the Alps was much higher than today. And we know that people were passing, for instance, from Italy to Switzerland through the Teodulo Pass. The Teodulo Pass is still covered by a glacier, even now, even after the retreat. And we know from oral witnesses that people could walk without touching any ice, without encountering any ice. And this occurred about 1100 after Christ. So you see that indeed this slide is showing how the vegetation may change, and this is another reconstruction that is the second one that I am presenting to you, which is interesting because it's like a zoom with respect to the previous one. I want to go to the previous one, just 1 second. This is the previous one. It's extended up to 500 millions of years ago. And then basically we are zooming in this part here, from number 4 to the right, okay, about 60, if I well remember, 60 millions of years ago, just 1 second. Okay, 60, yeah. And look at the scale. The scale is logarithmic. So we have a zoom in for the present, and you see that even 2005 is shown here with the predictions at that time. And then here we are around, the scale is kilo year before present. So here we are around 1900, and then 300,000 years ago, and then here million of years before present. So when you look at the slope of these changes in climate, take into account that the scale is changing, is logarithmic, okay? And so the slope is not preserved, the slope, the gradient of temperature change. What you see here is the anomaly on the vertical axis. 0 is the average temperature in in the past 10,000 years. Okay, and we can find here more or less the same pattern that we showed in the previous one, but here there is more detail, and you can see here the variability, and you can see here the source of the data. So, for instance, here you see references. This is prediction, reconstruction, and prediction of current climate that was derived by the model, the CRU Hadley model, T4. And then here there is a reference, Marco et al., which provided this reconstruction. This is another reconstructions provided by NGR-IP. And then here the reconstruction based on the EPIC-ADOM C, it's a drill, an ice drill. And this is the reference to the paper that provided the result. And this is a reference to another paper. And here we are in the early Holocene, mid-Pliocene, and here we are in the mid-Holocene. So it's important to see here, first of all, you see with different colors, different reconstructions. To some extent, they are overlapping. So where they are overlapping, you can see more than one signal with different colors, because the color corresponds to the citation. You see the citations have different colors here. And you see that in the Holocene, so the period that started 11,000 years ago, we have a quite stable situation. Characterized by a quite stable situation, characterized by a general increase of temperature in the first part, and then a general increase because the Holocene starts around here, 11. So you see that there is an increase and a period of stability, but beware of the scale, because here the scale is rapidly changing. So this period of stability is not really as long as you could perceive from the graphical visualization. And also the overall length of this period, which is about, I would say 9,000 years. The overall length, if you go back here, you see other periods of stability, which look like they are shorter, but they are shorter because it's the scale that is changed. It's logarithmic. On the other hand, we are interested in this period because it's the period of agriculture and civilization. And so this is the year 0, I think. This is the year 0, and this is a period that is already covered by civilization. If you think to the Egyptians, they were living about 3,000 years ago. So basically, what can we say here? What can we say is a distinguishing feature of the period of human civilization? A distinguishing feature is a relative stability of climate. And there are, oscillations. We will see another graph with a further zoom over here. But actually, this is a relative period of stability, indeed. And even if you include the global warming period, it's still a period characterized by small perturbations. This doesn't mean that we don't have to be concerned by climate change. Absolutely, we have to be concerned. But what is also important to take into account is that natural variability, let's call it natural, because a volcanic eruption, is it natural? Yes, it's natural because it's not human induced, but it's it's something that is infrequent. It's not really the norm, okay? Anyway, natural variability is also very important, plays an effect. This is the key message that is delivered by this graph. Here you see existence of the Homo sapiens back to about 500,000 years ago, existence of humans back to now we know it's humans, they go back to 7 million years ago. And humans had to cope with changes in climate, that natural changes in climate that are indeed very relevant, and more relevant, of course, than the changes that we are experiencing today. The question is what's going to happen in the future, and to what extent human influence can, in a way, interact with this natural variability. It's clear that there is the potential for natural variability to well compensate the human effect. But it's also clear that if they get in resonance, so if human influence is synchronous, there is synchronization of phases between natural variability and human influence, that may be a problem, because human influence has the potential to resonate with natural variability and accelerate some processes. What is the concern? The concern is another big extinction. And like the extinctions that we already experienced, that the Earth, not we, the Earth already experienced. And keep in mind that when there is an extinction, as I already said, the elementary form of life have more chances to survive. The form of life that are more developed, more, in a way, more complicated, they have less chances to survive. So this is the concept, of course. And this is why climate change is deemed to be a challenge, because a potential challenge, because it may cause, if not an extinction, it may cause a difficult situation for certain species to survive. And, you know, natural selection is not a good thing. It's not a good thing. Natural selection, it is something that we think it's related to nature, so it's nice. It's something that is in the order of things. But if you think the meaning of natural selection, it is the opposite of equality. It is the opposite of equality of opportunities. Natural selection means that who has the means, who has a physical strength, who has some opportunities survives. Who doesn't have the same opportunities don't survive. So it's something really that, even if it's natural, it's not really nice. And in general, nature, keep into account, nature in general, it's not really nice. If you think at the very pristine conditions, like the region here, in very pristine condition, it was a big marsh where living was impossible, and people to settle down here and to drain everything. So now there is nothing natural here. Where is the natural environment still there? In many places, but think at, north of Canada, think at Siberia, think at Himalaya. I mean, it's not so nice. We need to reach a compromise. And of course, the compromise means human influence, but in a sustainable way. And this is why sustainability, the concept of sustainability was created, not to deny the need for progress. We need progress, but we need a sustainable progress. Okay, and here you see that the next slides are marking interglacial period, etc. There is a question in the quiz that I'm not sure it refers to the conditions in the current period during the Holocene. Has the Holocene been characterized by a substantial increase of temperature or whatever? This question is, I need to revise it because I don't remember exactly. This question is often often mistaken. The students very often make a mistake in answering to this. I will give you more details because I want also give you an example of quiz in during the next weeks. So you will get some sample questions which will help you, which will guide you through, and maybe the same questions are also included in the final quiz. So it is a useful training. Okay, this is a picture of the last glacial maximum shorelines, Mediterranean area, minus 120 meters below present sea level. I like it. It is nice, and it shows that Sardinia and Corsica were connected. It shows that the Adriatic Sea was like a small pond. I am exaggerating, but you see that it's indeed interesting to see. And Greece, the number of islands in Greece was much lower because it was more extended the land area. It's nice, and it's derived by a paper in 2016. Of course, there is uncertainty. I think they simply took the current topography and lowered down the sea level. But of course, if you go back 11,000 years, maybe that the topography was a bit different. Also the topography of the sea bottom, because I mean, 11,000 years is not really a long time, but still, I mean, it is something. If we look at the topography, for instance, of the Alps in the past 11,000 years, it's changed. Not much, really, but there are changes. And because, you know, there are volcanic eruptions also in the bottom of the ocean, and there might be also shocks, events that are basically changing the topography, but the idea is clear. And this is another example of isotopic records. I am skipping these slides, and these are providings, other reconstructions, and I don't think it is telling us much more. So I'm skipping these slides here. And this is another analysis of interglacial period, and raises the question of the stability of the temperature during the Holocene, and introducing our next slide. And this is actually the slide that explains, introduces the question that I mentioned to you before. So are the last 10, 11,000 years the Holocene so stable? So high resolution stable isotope records from Greenland ice cores show minor oscillation. So a millennium scale, I mean, there is variability at the millennium scale, but still it's not very important. So in general, it has been indeed a period with quite a stable temperature. And as you see from this graph, and here it's a map of the climate anomalies during this event that occurred about 8,000 years ago. And in the previous slides here, you see it's this one. And basically here it's the map with a warmer temperature in the Southern Ocean, in the Southern Hemisphere, in the ocean in the Southern Hemisphere, a colder temperature in the Northern Hemisphere, and then the changes in terms of drier and wetter weather. These are the results of recent studies. I mean, they basically provide information on smaller scale, smaller variabilities with respect to the huge changes that we observed in the past, smaller variabilities that were experienced in in the relatively stable period of the Holocene. And you see what's written here. Less expected changes are more damaging, of course. And I also would add that the changes that occurred rapidly are more damaging because there is no time for the socioeconomic context to adapt. And this is the slide with which I wanted to close this lecture. And it is another zoom in over the past 2000 years. Okay, let me just check how many slides still I have to finish. Okay, no, I think I have to continue with the next lecture, but I wanted to finish this one because the next slides are providing possible explanation for these natural changes. So this one is interesting because it closes our cycles of zooms. So Holocene, a period with relatively stable temperature, and then with some cold periods, and then the final part, up to present, meaning up to present part of the Holocene, with a zoom on the past 2000 years. And here you see three distinguishing features. The Roman warm period. This is the period where I mentioned to you, people were crossing the Alps without touching any ice, without seeing any ice at the level they were walking. It is called the Roman optimum. Okay, and there is also say that Hannibal passed the Alps with elephants without any problem. It wouldn't be possible today because of the glaciers. And some people say this is misinformation, but actually it's not misinformation. Indeed, the Roman Empire flourished because there was the Roman warm period, and it helped a lot. And it looks like when temperature decreased, it was about you see, it's 0 is here, so it's 1500 years back when the temperature decreased. It was the time the Roman Empire collapsed. So there is a clear correlation between the prosperity of the Romans and the temperature. It's clear, and it's not surprising. And then there was a period from 500 to 800, a period that was terrible. It was cold, several floods, and it was a recession period. And then we had the medieval warm period, and the medieval civilization flourished. And it's not clear what caused these warmer periods. It's not really clear. And then after the medieval warm period, we had the Little Ice Age. The Little Ice Age that lasted, the peak was in around 1700, 1750. 1700 was the peak, but still 1750, it was quite cold. And then the temperature started to increase again, even before the Industrial Revolution. It started in 1750 to increase again. And this is a picture of the Venice Lagoon. In 1789, the year of the French Revolution, it was a terrible winter and people were skating over the Venice Lagoon. This is something that we have only this report. It seems like it's the unique event of glaciation of the Venice Lagoon that we know. It was indeed something that was remembered. And I also want to report that in the northern part of the Apennines, now there are no glaciers. There is only one glacier in the Apennines, over the Gran Sasso. Gran Sasso is the highest peak in the Apennines, is almost 3,000 meters. And there is only one glacier in the Apennines, and it's there. It's shrinking, it's disappearing. If we look at the northern Apennines, we are the last witness of a perennial snow accumulation around 1750 by Lazzaro Spallanzani. Lazzaro Spallanzani went in the summer in the northern Apennines. Northern Apennines are from Colle di Cadibona in Liguria up to Bocca Trabaria. It's at the boundary between Emilia-Romagna and Marche, I would say. And in this part of the Apennines, the latest report of perennial snow dates back to 1780, I think, Lazzaro Spallanzani. So it's interesting to take into account this variability during the past 2,000 years that was reconstructed, by the way, by isotope composition and also supported by traditions that were orally perpetuated and generation by generation and by diaries of monks. Okay. Let's stop here, and then we will discuss next time potential causes of natural variability. Any question? Good, thank you. I am closing just 1 second the recording.